Yeah. So yesterday we were talking about this example, and we were writing the admittance matrix. So very quickly, somebody can help me to writing down admittance matrix. So first of all, how many nodes are there? Yeah. How many nodes? Do you agree with 4 nodes or yeah? You had some problem in nodes. Maybe I can make new circuit. It's better to have new circuit. Yeah, so some network I made. So you need to write down the impedances, and before that, as we agreed, there will be two sides, left hand side and right hand side. Left hand side, you are going to have all the currents which are flowing through passive components, and right side will be the one which will have all the currents. And when you are writing left hand side and right hand side, you are going to have following things. So as this book is following J, so I am writing current here. Let's call this one also J. J is current, right? So, is there anybody who can help me in finding out the number of nodes? Yes. Now, how many nodes are there? By the way, let's keep this one as ground. I'm waiting for your answer. By the way, 3. So this is 1, this is 2, and this is 3, right? Huh? Is there anything missing here? Okay, so there are three different nodes are there. So you can write down the admittance by 3 things: 1, 2, 3, 1, 2, 3. So what will be y11? Y11 is the one which is with respect to 1, all the current coming towards node 1. That's what you need to write down, and all the entries will be in positive. Yeah. No, J1, J2 will not be coming, right? That is what we agreed. Left hand side, all current which is passing through passive components. Right hand side are the currents. Yeah. So SC1 plus 1 by SL1, huh? 1 by SL2. Anything else? No, right? So those which are related to node number 1 are these 4 branches. That is what written here, right? Okay. So current we are not writing because it will go to the right hand side. So what about y12? So y12 is the one where between 1 and 2 node minus 1 by SL1 minus SC1, right? Anything else? No. What about y13? Yes. 1 by SL2. Okay. So y21, Akshita, y21. Are you following or no? Following, then can you tell me what is y21? Hmm? Okay, minus SC1. What about y22? Somebody new guy. Okay. Left. Yeah. Y22.
Minus 1 by R1.
1 by R1.
1 by SL3.
1 by SL3,
1 by SL1 plus SC1.
right? All the entries will be positive because you are at Y22, right? Diagonally, all entries will be positive, right? Okay. Now, what about the last entry? Y23, Divya, Y23 minus 1 by SL3. Okay. Y31. Somebody from Komal or minus 1 SL1, SL2, sorry. Right? Is there anything? No. Okay. What about Y32? Aishwarya. 1 by SL3. Okay. What about the last entry? Somebody. 1 by SL2 plus 1 by SL3 SC2, right? That's it. So times all those voltages is equal to all the currents, right? So this is V1, V2, V3. What about these currents, by the way? Hmm? J2, you have to look at the first node. So J2 minus J1. What about J1, J3, right? No doubt, right? That is how you can write down the like equations using admittance matrix, and thereafter you can solve the these kind of matrices. So we are going to solve these matrices maybe after learning two more chapters. One is called graph theory and one is called two-port network. Then we will go into the detail for this. But before that, let's become expert on uh, writing the admittance and impedance matrices, right? So this is easy, right? You can write down, even you solved it also in past, you have solved it, yes or no, Gaurav? You solved such equations using Kramer's, yeah, yeah, Kramer's rule. You have solved this. We'll do this, we will revisit it, but let's assume that you, whether you know or not, but we are not breaking the learning path. So which says that we should complete the admittance matrix also. But before that, there is something called voltage to current transducer. Do you understand this word called transducer? Have you ever heard transducer? What is that transducer? Hmm? Converts. Yeah, Ankita is saying something. So what you are saying? Yeah, converts one form of energy to another one, to another, right? Even resistance is also one transducer which converts voltage to current, and capacitor, inductor, there are many other things are also there. So I am talking about VCT, which is voltage to current transducer. I am using this word because the book which I am following, so those who are, so I am following this book now for this chapter. It's black, Ziri black, right? So it's online is available, right? I don't know whether it's available in our library or Vijender, is it available in library? Okay, I'll give you soft copy if you want. But it's downloadable, right? You can go to some pirated place, right? Right. Okay, so this is VCT, voltage to current transfer. But there is another word which is very popular, which we call voltage control voltage source. Okay, that is a mistake here. I should have written voltage controlled current source. That has to be there. At the output, current. By mistake, I wrote VCVS, but it's VCCS. So at input side, I am giving voltage. Output, I am carrying the current. When I want to do that, voltage control current source. What is the characteristic of voltage control current source in terms of input impedance and output impedance? Infinite input impedance and low means zero output impedance, or you can say that some finite value, and some value which is greater than something like 10 kilo, 1 kilo, we'll call it very high value. So you can see here, if you are looking into the system, if you are applying the known Thevenin voltage here, what you are seeing inside, is it infinite or something else? Okay, yeah, right. So that is what we need to follow. What I wrote was voltage control voltage source. That was by mistake, right? So that has been made here. The input side there is an open circuit. Output side there is a current. That current is G times Vi minus Vj. That means that G is transconductance and the voltage is difference of two input voltages. And such current is known as dependent current source. Till now you have seen independent current sources. Independent current sources are the one which are fed through function generator or through power supplies, right? But dependent current sources are the one which are dependent on the dynamics of your circuit. Like Vi and Vj will change, then current will change. This kind of circuit is known as basically field effect transistor. This is the internal diagram or the equivalent model of voltage control current source, which is field effect transistor. Have you heard about this ever? No or yes? How many heard about this? Can you raise your hand? Word, okay. Huh? Like MOSFET, right? Yeah. Like MOSFET, okay. JFET, yes. Right. So such FET is here. So this is field effect transistor because the input is voltage. It's controlled by field. BJT is the one which is controlled by current, right? So it's current control current source, but MOSFET is voltage control current source, or the input is field. Hmm? VI? What is VI? You mean to say? This one is VI and this is VJ, right? Okay. Now I want to find out the relation because I have four different nodes, right? Vi, Vj prime, Vk, Vk prime, right? I have four different nodes are available, right? And I can write down those equations in terms of currents, right? So if you are applying KCL, you can find out the current equations because Ij is equal to nothing but 0, Ij prime is nothing but 0, Ik is nothing but its positive direction G times Vi minus, sorry, it's Vj minus Vj prime, and Ik prime is equal to minus G times Vj minus Vj prime. Are you following these equations? It's written from here only. But rather than doing this, we can also apply the admittance matrix if you want, like so. Can we write down 4 4 by 4 matrix which is Vj, Vj prime, Vk, Vk prime, Vj, Vj prime, Vk, Vk prime. Can we write down that? Admittance matrix I am talking about. 0, right? So J to J, there is no current flowing, right? There is no passive component available in between. What about Vj to Vj prime? It's again 0. This is also 0. This is also 0. Vj prime and Vj 0. Because this side there is no impedance is available. Hmm? Infinite. Impedance is infinite, but we are writing admittance, by the way. It's 1 by infinite. That's why I'm writing 0. Yeah? So what about next part? VK and VJ. VK and VJ. When we are seeing VK and VJ, at that time other nodes are 0. At that time other nodes are 0. Effect of VJ on VK. It's G times VJ. Can you see? It's G times Vj. This current flowing through this one is G times Vj. So the admittance which is seen in this path is equal to G, transconductance. Right? Hmm. Vk prime, what Vk prime? No, no. This current is flowing because of this guy. That's why I kept this intentionally. So it's this current is Vj minus Vj prime. Because of these two nodes, it's happening. Sorry, Vj and Vj prime. So this current is flowing because of these two, not because of Vk and Vk prime. It is happening between Vk and Vk prime, but this Vk is depending on Vj node and dependent by G times Vj. So K is equal to G times Vj. Just I am writing for the this particular matrix entry. So it's G times Vj. So I can remove that Vj. I'm going to keep it here somewhere. Right? Current will be here. So this is G. Vk and Vj prime minus between Vk and Vk 0. Right? This is also 0. What about Vk prime and Vj? Vk prime and Vj minus Vk prime and Vk prime. Sorry, Vk prime and Vj prime. So it's and others are 0. Right? Yeah. I'm doing this because we are going to use this somewhere else, which will be the bigger circuit, which will have MOSFET in your circuit. Okay. Now let's assume that this is a circuit which is actually a MOSFET, which I'm going to call that one as transducer, which is converting voltage to current. Right? Now can we write down different equations? Because now look, this circuit does not have any transistor. There is no transistor, but we are actually analyzing the circuit which has transistor. Right? So can you tell me what will be the if V0 equal to 0? If you don't want to consider V0 equal to 0, then you need to take another terminal which is ground. Can we write down 1, 2, 3? So 1, 1, Y11. So none of the entry will be minus when it's Y11, Y22, Y33. All the diagonal entries will be positive. Right? That already we observe. Right? So now can you tell me G1 plus G2 plus G5? Okay, right? What about now 1, 2 minus G2? That's it, right? Right? Now what about 1, 3? Okay, minus G5. What about 2, 1? Minus G2. As you have observed, it's similar entries which are here, it will go here at the down, right? What about 1, 2, 2? G2 plus G3. Anything else? What about this one? right? 0. So 0 is 0, so I am not adding this, right? Now what about other entry? Like 2, 3. Between 2 and 3, minus G3, plus, right? There is no entry because of this current, because that current is happening at the node 3. That's why we are not considering this right now. And look at these two currents. J is independent current source and GV2 it's dependent current source. Dependent current source will be part of our admittance matrix, right? So now, can you tell me what will be the 3 1 minus G5, right? G3 2 minus G3, hmm, right? Anything else which is left? No, right? Because 3 and 2. Now you have to write down for the last entry, which is 3 3. So let's start from G4 plus G plus G3 plus G5. Anything is 2 3, 2 and 3. Last one. Oh, that is minus G3 minus. Between 2 and 3, I can see only one element. No? Yeah, so that is what I was explaining. Uh, between 2 and 3, when we are seeing this effect of 3 on 2, actually, we are not seeing the effect of 2 on 3. When we are looking at this row, it's all about effect of other nodes on the 2, right? So here G is not happening, right? Okay, right, all good. So okay, only one mistake. The current is going down, so it has to be plus, right? Current is going down. Next slide. Okay. Hmm? 3 3. Which one? Oh, last one. Oh, that was another mistake, because the mistake is there. The reason is because when we are looking at 3, all other nodes are 0. So this V2 is 0, so it's 0, right? So that was mistake. Right? Okay. So
If we have written it, the positive one is V2 and the bottom one is V0, so the current at that point will be small g into V2 minus V0. Then we would have written here G.
no, but others are 0, right?
If we not consider
Yeah, yeah. If you don't consider, but the whole theory of admittance matrix is based on one fact. When you are writing VII, means I node will be positive, other nodes are 0.
so
Hmm.
why the last G and
Sorry?
why
Okay, because current is going in different direction. If it is coming towards it,
towards
yeah. Right? So now there is something called hybrid pi model. Have you heard this word? Okay. So all the things which are like this, pi is pi, right? So if you have a network which has been connected like this, have you seen such networks? Yeah, ladder network. Yeah. All these are look like pi. So it's a cascading of pi. You know cascade, right? You know cascade? Yeah. Series like one after another one. That is called cascade. I'll introduce one word just for your information. Do you have any Bengali here? Any Bengali student? Do we have any Bengali? Because like I I used to say this joke even when I'm teaching analog course. Like when I was during my like MTech time, and my professor was saying that cascode. He used to say cascode, and I during my BTech I only heard cascade. So I thought he is Bengali, that's why he is saying cascode. But cascode is another topology. It is not Bengali version of cascade, but cascode is different than cascade. Cascade is one after another one. Okay. So cascode you will see maybe up in future. You will see cascode also sometimes. Okay. So cascade is the one. If you are connecting this circuit with another circuit after this one, it's cascade. Okay. And all these things are with respect to ground only. So such kind of models are known as hybrid pi model. Actually, let's call it pi model. Have you seen delta star connection? Those are not pi. Right? There are many ways to design circuit, or you can realize them. Right? This is star. There is some delta. So this, the one which we have drawn just now, that was pi model. When I'm saying hybrid pi model, there are two things. One is low frequency model, and one is high frequency model. So low frequency model, I'm asking you a question. What are the passive components you can have at low frequency? Passive components, there are only three. Fourth one has invented, but we are not using in books. So, right? Three RLC, right? Passive components. So, which passive components you are going to see at the low frequency? Inductor, okay. Resistor, right? But for a like time being, we will not involve into inductor. Let's call just resistor. And at high frequency, capacitor, resistor, right? So when we are drawing the model, which is hybrid pi model, if it is for low frequency as well as for high frequency, it's called hybrid pi model. It will have both. Just now we have found out, or we have drawn one model. This has only resistance, something is open. How this has been derived, it's part of different course, analog course. So we are not going into that, but it will be equivalent of this one at low frequency. Now if I want to draw same thing at high frequency, what I need to add? Capacitors, right? So where are the capacitors? If this is gate, this is source, and this is drain. So these three terminals are known as gate, source, and drain. So there are two dissimilar plates, then you have to add a capacitor. Let's make this capacitor here. The name this capacitor as CGD, gate to drain. You can name this capacitor as CGS. You can name this capacitor as CDS. Right? Can you see this, right? The name has been given on the basis of, if the capacitor is between drain to source, we are going to call it CDS. If it is between gate to source, CGS, gate to drain, CGD. Right? So that model I was talking about. And there will be one extra resistance. Let's understand this one as a load resistance for a time being. It's a load resistance, which is between drain and source. So can you see this model? If you want to replace this complicated element, you need to transfer it to this one. Between all the plates there are capacitors. Between drain and source there is one current, because this is voltage controlled current source, or VCT. This book calls this one as VCT, and some all other books are calling this one as voltage controlled current source, which is input is voltage, output is current, means input impedance is infinity, output impedance is also infinity. If you want to check it, we can check it. So when we want to find out these impedances at low frequency, so let's call this one as VGS. When I'm writing VGS, it's equal to VG minus VS, right? You are aware of this, right? If it is VBE, it's a base voltage minus emitter voltage, right? You are aware of these notation, right? Now, Divyanshu, can you tell me what is the input impedance using your Thevenin theorem? Infinite, right? So input is infinity. What about output? You have to apply same theorem. So what Thevenin's tell you to do? All the independent sources, voltage sources, will go to 0 or like short circuit. So it will go to 0, right? All the independent voltage sources will go to 0. Output terminal is open. By the way, you are looking at the output impedance at output terminal. So what are you going to see? So what are you seeing inside this network at the output side? Yes. Anything from back? What are you seeing? Huh? Why infinite? That is what I'm asking. VGS 0. Excellent. Right? But most of the people are making mistakes. So those people who are seeing those people who are seeing transconductance G, that's wrong answer. Some people can see and say that it's a transconductance, right? But the answer is wrong because when we are doing this, all the independent sources are 0. So VGS is 0. So this current is also 0. So if current is not flowing, means the output side you will see infinite. If you are seeing input impedance infinite, output impedance infinite, then you are going to call such circuit as voltage controlled current source. Or you can also call that one as VCT, which is converting voltage to current, right? But if you have a system, I'm drawing the small signal model or the pi model for BJT. So can you tell me what will be the input impedance here? This is in some ohms, right? Output impedance infinite, right? So this is something in ohms, you can call this one as low. If input is low, output is infinite. Akshita, current controlled current source. Input is infinite means voltage. Input is low means current, right? So there are two different communities in like on internet. You will find some people who are circuit designers and some people who are device physics people. So physics people say that this is current instead of current control, it has to be voltage because we are feeding voltage. But like as I am also circuit designer, I don't follow that, right? As per circuit theory, all circuit designers say that this is current controlled current source. All like there is a there is a guy whom I follow, you know. So there is a book called Behzad Razavi. He wrote almost like 10 books on different analog circuit designing, even for ADC, PLL, many things he did. He is considered as like Newton of our analog field. He is also calling this one as current control current source. But all the physics people are calling different thing. But we are having reasoning that if input impedance is low, of course it has to be current. We are going through some reasoning. We are not saying on on paper that we are adding voltage, so this is voltage. It's not going that way, right? Anyway, so if that is the case, can we quickly write down the admittance? So now I am not going to help you. So how many nodes are there, by the way? If source is not 0, then 3. If source is not 0, if source is 0, let's keep the things simpler. Then source is 0, then it's 2, right? But let's keep the 3 nodes and then write it down, and you will have bigger admittance matrix, right? So what will be, YGG, I should say. So similarly, you can write down others. So everything is written in terms of Y, which is admittance. Okay, so maybe you can check those things. I am also skipping this part for just for. So once you have all the passive element thing, um, can you draw the admittance matrix, right? Without having any problem, it's very easy. Okay, there is one more thing, something called planar network and non-planar network. Have you heard about this? Okay, so all the network where between, like, there are many nodes are available, but if those nodes are not, like, let's assume that these are the nodes 1 2 3 4 5, all these lines are not just line, but there might be some impedance in the form of inductor, resistance, capacitor, or maybe the series or shunt combination is in these box. If those elements are crossing each other, you can see this element is crossing this, is crossing this, right? Sorry, not this one. Yeah, if they are overlapping, we are going to call that one as non-planar. If it is not overlapping, it's called planar network, right? Connected, right? So anyway you want to look at this, but if you are, so in future we are going to draw some planar and non-planar graphs. The graph will look like this one, not the one which we have done previously, right? Okay, unfortunately we could not cover finite state graphs, but that you can learn it if you are so much interested in digital side. You need to learn something called finite state machines. That will be part of automata theory, right? So you should take that course if you are interested in digital side. So I'm not going to touch that because that's not going into our circuit, right? But you can use it, that finite state machine, in digital course. Are you taking digital system design? So you are using FSM somewhere? Huh? Okay. So that is most important part, right? Okay, so as we have written uh, admittance matrix using nodal formulation, you can also write impedance matrix using mesh analysis, because this analysis is all about currents. So there are 4 different currents, right, in this given circuit, right? So, and I can write down 4 equations for 4 currents. Those who forgot, I can see I can write it down very quickly. So it's Z1 times I1 plus, so I'm starting from here, Z1 times I1 plus Z2 times I1 minus I2 minus E equal to 0. Generally, I do this one. I don't. Right? Both are same, right? So I generally follow the left hand side and right hand side. Okay, so similar to the previous case, left hand side and right hand side. So this right hand side, all the independent voltage sources will be here. Left hand side, all the passive components. So the voltage across all the passive components will be written left hand side. No, no, lecture is important, right? Hello? Yeah. So the passive components you need to see, and across that you need to write down the voltage, right? So this is the first equation. You can write down the second equation starting from Z2, I2 minus I1, because I2 is powerful than I1 when you are talking about this loop, but this component is being shared by 1 and 2 both. So it will be I2 minus I1. Do you want me to write down separately, or are hmm? Let's assume that we are going to write for this loop, okay, only for third loop. So can you help me for writing this? Z5 I3 minus I2,
plus Z4
I3 minus I2
plus Z6 I3 minus
plus Z7 equal to 0, right? So by these equations you can write down a matrix, right? But here also there is an observation. All the diagonal entries are actually positive. All the diagonal entries are positive. Others are negative, right? One more thing. When you are writing these equations, you are not going to write about the nodals, but you are going to talk about different currents. And right now we are writing impedance matrix, not admittance. So the unit of each component will be ohms, not uh, 1 by ohms, right? So now between I1 and I1, just okay, where is that? Yeah. So I1 current is flowing through how many components? These two. So you are going to write down Z1 plus Z2 in the position of I11, right? Both the, when I'm interested in writing down this one. Now I'm interested in, let's say, Z22, which is coming diagonally. So Z22 current I2 is flowing through how many components? Z2, Z3, Z4 and Z5. So you need to keep that thing. Z2, Z3, Z4, Z5. Similarly, can you tell me about like Z33 component and Z44 component? What is Z33? Right? 5, 4, 6, 7, and this will be 3, 6, 8, 9. But in other entries, when it's Z1, 2, right? Hmm? Minus Z2. So it's shared by this one. So you are intelligent, right? So you can observe this thing, and through which you can write down this impedance matrix as well. So whichever way you like, if you are following impedance, it's mesh analysis. If you are following uh, like voltage, means nodal analysis, it's admittance matrix, and through which you can solve any equation. Yeah. E is at the first side, right? It's between, it's in the first loop.
if it is between 1 and 2, then we write for 1 and 2 both.
Where 1 and 2?
Like under Z2 it is.
you are seeing here. Yeah, then you have to keep one more voltage that side also, right? Right. Right. For one. Yes, yes, it will be added in. Yeah, it will be added and it will be subtracted. You have to take care of two things. If you remember, we have written one matrix also, right? In terms of where it is, I need to find out. Yeah, here. So these currents were found out by Divanshu, and he told me J2 minus J1, J1 and J3. In this position, we got two currents, J2 minus J1. So same way you are following here KCL, there you have to follow KVL. So what you are saying was correct, right? If there is an extra voltage, you need to accordingly add it or you have to remove it. But this, all these things are on one assumption, that all the initial conditions are zero. That is what we agree at the beginning itself, right? Because this is going to be used in the computer. We are developing a simulator which is going to simulate this circuit, right? So how that simulator will start the simulation, then you have to write accordingly. But if there is an initial condition, how to do it, that we are going to add maybe in the later stage, maybe after 20th lecture I'll tell you how to do that. Yeah, so these are the observations already, you know, right? So then that's the completion of admittance matrix and impedance matrix. Tomorrow onwards, okay, from Tuesday onwards we are going to study graph theory.